Hello, everyone. This is Lance Lian, Professor of Biomedical Engineering at Penn State. Today, I'm going to share with you some differential equations. So as you know, differential equations, we have ordinary differential equations, the so-called ODE, and we also have the PDE, partial differential equations. When we say ODE, we'll more talk about you have one x that will generate one y. So for example, a typical example of ODE would be dy over dx equal to x, or we have dy over dx equal to y plus x. So in these equations, when you have one x, you will generate one y. So these are called the ODE, ordinary differential equations. For PDE, we have two variables that is corresponding to one y. So for example, we can have y as a function of x and time t, okay? So this is pretty typical in mass diffusion. So in mass diffusion, when you give a certain position x at a certain time point, and you can generate a concentration profile, okay? So basically, y is a function of x and t, okay? So today, we're going to talk about a very special equation called a Bessel equation. Okay, so first of all, Bessel equation is an ODE. That means if you have one x and you will generate one y, okay? So in general, the Bessel equation look like this. Okay, so why Bessel equation is so important is because Bessel equation can be used to describe mass transfer in the cylindrical coordinate, such as you have let's say you have a blood vessel, and we treat the blood vessel as a cylinder, right? And then on the surface of the blood vessel, here you have endothelial cells. And these endothelial cells is going to make nitric oxide, the NO, is going to make from the endothelial cells. And once they make the NO, and they will diffuse both into tissue and into the blood. So in this region is the blood, okay? So you can see the diffusion direction is in the radial direction in cylindrical coordinates. So that's why, you have something look like this, okay? So why you have this? Remember, for the diffusion term, right? For the diffusion term, in cylindrical coordinates versus the diffusion term in spherical coordinates, right? In cylindrical coordinates, inside of this, you have the x, right, or r, right? So, but in the spherical, what do you have? Inside of here, you have the x squared or r squared, right? So that's why, this is very, very important. It's not like a random ODE equation that we are interested to solve. This equation is a very, very important equation, okay? Not only it's important for mass transfer, it's also very, very important for heat transfer, okay? So for this equation, N determines the order of Bessel equation. Okay, so if n equal to 0, and then we are going to say this is 0, this is 0 order of Bessel equation. Okay, so if n equal to 0, what we got here is x dx x dy over dx plus m squared x squared y equal to 0. Okay, so this is called the 0 order Bessel equation. Okay, so now depends on the the sign before the m squared. Okay, the sign before the m squared. So if the sign here is positive, if the sign here is positive, then we call it like a, the Bessel's equation, right? Bessel equation. And if sign here is negative, we call it modified Bessel equation. Okay, modified Bessel equation. Okay, so in the example that we discussed about the nitric oxide diffusion, what we have is we have something like this: R dr R d concentration over dr. So this Ci is the concentration of the nitric oxide, okay? And then minus the K1 over D1 times R squared times the Ci equal to 0. So if you look at this equation and also the Bessel equation, so this is the Bessel equation, right? So clearly, what you can see here is because this is negative, right? So then this is a modified Bessel equation, okay? And then clearly m is equal to square root k1 over d1, okay? K1 over d1. So for equation like this, the general solution is Ci equal to a linear combination of two functions. Okay, the first function is called the IOX. So in this case, x is the square root k1 over d1 times r. Okay, and another function is the ko square root of k1 d1r. Okay, this is because a general solution for this guy is a linear combination of IOMX and the KOMX. Okay, so this M is this, right? So M go here, and then X in the example is R, right? Okay, so when we say the general solution is a linear combination of two functions, right? So before each of the function, so we are going to have like a constant number, right? So in this case, let's call it A and B, right? So let's say like you have two constant number, A and B, right? And then A and B will be times each of them, right? Times the first one is IO, R K1 over D1, right? Plus B also times the KO, R times K1 D1, okay? But then the next question is, how do you determine A and B, okay? When you try to determine A and B, now you have to use the so-called boundary conditions, right? You have to use the so-called boundary conditions. So in this case, one of the boundary conditions that we can have is, let's say we consider the NO nitric oxide diffuse into the center, right? And then here, on the surface of the endothelial cell here, it's also diffused into the center. So we can have when R equal to 0, the dCi over dR is equal to 0 because of the symmetry, right? Because of the symmetry. That means, Ci is equal to a number, let's say that number is E, okay? Is equal to a definite number, okay? Is equal to a definite number. Okay, so then based on this, we can kind of determine like A or B, okay? So first of all, in order to determine that, we needed to know the pattern of IO and KO, okay? So if this is the MX, if this is MX, so this is the IO MX, and this is the KO MX. So the curve look like this, okay? And then this one look like this, and then approach to 0, okay? So based on this, we know when R equal to 0, so then this thing will become 0, okay? So that means we are looking at here, okay? We are looking at here. So you can see, we know that the Ci at R equal to 0 is certain number, is a defined number. But the KO, when MX approach to 0, this number become extremely large. It will become infinity, okay? So then you cannot make it become infinity, because if it's infinity, then Ci can become infinity. But the reality is Ci is a constant number, okay? So then what can we conclude based on this? We can conclude that B must be 0 because we want to get rid of the KO, okay? We want to get rid of the KO. And then, so eventually, the final expression for this simple problem would be the Ci will just equal to A times the IO R times square root K1 over D1, okay? So I hope this short video helps you understand, what is the Bessel's equation, okay? So if you have any questions, leave your comments below. And don't forget to subscribe to the channel. Thank you. Bye-bye.